Okay, so we're going to try something new. This is a self-paced lecture, which means you're watching a video recording of me going through the lecture notes, but you can stop and pause and replay different sections of the presentation as you choose. I recommend that you take notes the way you normally would, but you can pause when you need to and move on when you're ready, as opposed to waiting for me or waiting for other people in the class. Additionally, you should write down any questions that you have to ask me later, or if you're completing this in class, raise your hand and I can answer it when you have the question originally. We're going to start out by talking about a unit of measure called the mole. Even though we normally associate moles with furry little creatures, there is actually a very important role for moles in chemistry. Let's begin. When we're quantifying matter, there's lots of different ways that we can talk about it, lots of different ways we can talk about units, and that's what we've been doing in dimensional analysis over the past few days. So if we consider something like a bouquet of roses, we can think about how many roses are in the bouquet and how do we know that? In this case, we could count the roses, and we could see that there are 12 roses in this bouquet. And if we were describing this bouquet, we might talk about the fact that it's a dozen roses. So if we look, there's a number of different ways we could describe it. We could talk about the mass. Maybe the roses weigh about 340 grams. We could say there are 12 roses, or we could say that there's 1 dozen roses. Dozen is a quantity. It's an amount of stuff that we talk about on a regular basis. You might buy a dozen eggs or a dozen donuts, and you know that that actually means you're going to buy 12 eggs or 12 donuts. The mole is like a dozen. It tells us an amount of stuff. Let's consider another example of quantifying matter. Let's look at a glass of water. How much water is in the glass? How do we know how much water is in the glass? What units can we use to describe the water in the glass? There's a couple of different ways we could do this. We could talk about the volume of the water, how many milliliters there are. We could talk about the mass, how much does the water weigh? And then we could start talking about it in more chemical terms. How many molecules of water are in the glass? How many atoms are in the glass? And if we do that, we can quickly see that we start dealing with very large numbers. So volume might only be 50 milliliters. The mass is 49.9 grams. But when we start talking about the number of molecules, we get 7.38 times 10 to the 23rd molecules. Or atoms is even larger. 2.22 times 10 to the 24th atoms. That's a lot of stuff. Those are really large numbers. So how do we talk about them? If we were to use common English terms, we could say there are 738 sextillion molecules of water. Or you could say that there's 2 septillion, 226 sextillion atoms in the glass of water. Those are really large numbers, and they seem kind of abstract. So we want to develop a way for dealing with numbers this big that makes it easier for us without scientific notation and without having to say huge, gigantic words like sextillion, septillion. That's a little bit excessive. So we have the mole. Not this mole, this furry little guy. This mole. A mole is defined as the number equal to the number of carbon atoms in exactly 12 grams of pure carbon-12. If you recall, carbon-12 is carbon with 6 protons and 6 neutrons. This sample of carbon containing exactly 12 grams is 1 mole of carbon. It tells us how much stuff there is. Just as an aside, in case you're curious, as I was, why the heck do we call this quantity a mole? This has nothing to do with ground-dwelling creatures. There was a chemist, a very famous German chemist, named Wilhelm Ostwald, and he worked to formally define this new unit, the mole, which many people had been working towards for many years. And when he discovered this unit and defined this unit, he named it mole, which is short for the German word Molekül. So in 1897, the mole was translated into English as mole with an E on the end, and so the mole was born. Here's a more concrete definition of our mole. It's defined as the number equal to the number of carbon atoms in exactly 12 grams of pure carbon-12. So in 12 grams of pure carbon-12, there are 6.022 times 10 to the 23rd atoms of carbon. If we wanted to write this as one gigantic conversion factor, we could write that 12 grams of carbon is equal to 6.022 times 10 to the 23rd carbon atoms and is equal to 1 mole of carbon. What we obtain from this is that 1 mole of a substance is 6.022 times 10 to the 23rd units. And we actually give this big number a name. This big number is called Avogadro's number. Avogadro was another chemist, and he started experimenting with this idea that there was a relationship between the amount of atoms or the amount of molecules in a substance and the mass or the volume of that substance. So this number was named after him. So if you hear me talking about Avogadro's number, I'm not talking about the Tasty Sandwich Shop. I'm actually talking about 6.022 times 10 to the 23rd units of a substance. We can quickly see, if we consider our water example again, why the mole is so handy. If we have 3.8 times 10 to the 23rd molecules of water, or 2.22 times 10 to the 24 atoms of water, that actually breaks down to just being 1.23 moles of water, which is a much more manageable number. Chemists love to deal in moles, and so you're going to see moles come back again and again for the rest of the semester, because it's so much nicer to say 1.23 moles than it is to say 7.38 times 10 to the 23rd. It's much more concise, it's easier to write in calculations, and has fewer opportunities for error. So let's talk about a relationship between moles and something called atomic mass. Atomic mass can also be called molecular mass as well. So if you hear me say molecular mass, I am talking about atomic mass as well. So here are two conversion factors that we discussed earlier. 1 mole of carbon atoms equals 6.022 times 10 to the 23rd carbon atoms, or 6.022 times 10 to the 23rd carbon atoms equals 12 grams of carbon. If we set these two factors equal to each other, so we have 12 grams of carbon over 6.022 times 10 to the 23rd carbon atoms, and then we have 1 mole of carbon over 6.022 times 10 to the 23rd carbon atoms, and we cross multiply like this to eliminate Avogadro's number, we can see that 12 grams of carbon equals 1 mole of carbon. If we rearrange this by dividing both sides, atomic mass of carbon is 12 grams per mole. This means that a sample of a natural element with a mass in grams equal to its atomic mass contains 1 mole of atoms. So the mass in the periodic table is the mass for 1 mole of that element. This is really useful, and I'm going to show you later how we can actually use this relationship in a very powerful way when we're solving problems. This is the end of the Introduction to Moles lecture. What we will do next time is some examples of using mole relationships to determine information about a substance. So we're going to study how to use molar mass to find out how many moles are in a sample of substance, and we're going to use molar mass and moles to determine how many grams a certain number of molecules might weigh, and things like that. If you'd like to go back and review this lecture, you can skip to any part and listen to it a second time. You are also welcome to review the whole thing to double check your notes.